Good afternoon, class. This is Mr. Holloway again. Hey, last video we talked about electric fields. So I was going to start off a little bit on this. Think about if we had two plates, and one plate was positive, one plate was negative. That means our charge would flow into the negative, as you can see as I've drawn by my lines here. And there's typically no electric fields inside of a conductor because that conductor that's around the wires or the plates or whatever. And a good example is, think of a battery. That stuff that's inside there and that stuff around it is kind of holding everything in place. So conductors shield space from an electric field. So there's not much of an electric field outside of it because the electricity can't get anywhere. Now, this here kind of goes in, and it's very similar to what a capacitor is. Okay. A capacitor is just something that's stored electrical energy. And if I increase the battery voltage, that means I've got my two plates, like up here in the top, they tend to be closer together. And the closer they are, the less force is needed for the electrons to flow back and forth to each other. So that means that there's a greater charge is stored inside of it. So that's kind of what a battery is. It's kind of a capacitor, stored energy. So let's shift gears a little bit, and these words we're fixing to use are going to bring back some memories. Since we're into electricity, we're going to talk about electrical potential. Okay, and back when we talked about potential energy, you should remember that that's energy that is stored or has the ability to do work. Okay, so electric potential is just the electric charge of something. How much electricity does it have the ability to do work? Oh, and another good thing to look at it is its electric potential per electrical charge. Now there's a formula that goes along with it. So let's say we have electric potential is equal to the electric potential energy over the charge, which that is equal to, or another way to look at it is volts per amount of work per charge. Now we go back and we could do a derivative, and let me just write the equation down. V is equal to work over charge, which is equal to force times distance over my charge, which is equal to basically the electrical charge, sorry, don't want you to get confused, times the distance over the charge, which is equal to the electrical distance. Or, let me change colors here so you can kind of get the idea. I can just say that it's the electricity is equal to the volts over the distance, which is equal to the force over the charge. So if I look at all this, I could lay it out anytime I needed to and use different variables to get where I wanted to. That's called a derivative. Or I can simply go back to this basic equation. This is why my volts is either measured in newtons per coulomb, or they're measured in volts per meter. Okay, that's why we need a voltmeter to measure our current or the electrical charge in something. But the main things I want you to stick with is you've got, hang on, I'm going to rewrite this equation right down here. You got volts is equal to the work done over the charge involved. Okay, that way you can see it. I don't know if you got it in the frame. But long thing short, I can derive everything from this set of formulas I have here. It's all measured in newtons per coulomb or volts per meter, and this is my basic formula equation here that I'm going to use when I'm looking at the electrical potential. Alright, that's all for this video. We'll see you soon.